Ever wonder how we went from thinking the world was made of just earth, air, fire, and water, to holding a supercomputer in the palm of our hand? The answer lies in a story of relentless curiosity, brilliant minds, and a revolution that happened at a scale so small we can't even see it. This is the story of how we cracked the code of matter itself. For thousands of years, the atom was just an idea, a philosophical concept of an uncuttable particle. It was a neat thought experiment, but that's all it was. Then, in the late 19th century, everything changed. A scientist named J.J. Thomson was experimenting with cathode rays, and he discovered something incredible. A particle thousands of times lighter than the smallest atom. He had found the electron. Suddenly, the uncuttable atom wasn't so uncuttable after all. It had parts. This discovery sent shockwaves through the scientific world. If atoms had parts, how were they arranged? Imagine a flurry of new ideas. Some thought it was like a plum pudding, with electrons scattered like fruit in a cake. But then, Ernest Rutherford's famous gold foil experiment blew that idea away. He found that atoms were mostly empty space, with a tiny, dense nucleus at the center. It was a miniature solar system. Niels Bohr refined this, suggesting electrons orbited the nucleus in specific energy levels, like planets in fixed orbits. The picture of the atom was getting clearer, and with it, our understanding of everything. While scientists were diving deep inside the atom, another was organizing the world of elements on a grand scale. Dmitri Mendeleev, a Russian chemist, was obsessed with finding a pattern in the elements. He wrote each element's properties on a card and spent days arranging them, like a game of solitaire. He noticed that if he arranged them by atomic weight, their properties repeated in a regular pattern. This led to his masterpiece, the periodic table. But here's the genius part. His table had gaps. He didn't see them as mistakes. He saw them as predictions. He boldly claimed that new elements existed that would fit perfectly into these spaces, and he even described what they'd be like. And you know what? He was right. Gallium, scandium, germanium, all discovered later, and they fit his predictions perfectly. He had created a map of the material world. With the atom structure and the elements organized, the stage was set for the next leap into the unknown. And that leap was taken by one of the most iconic figures in science, the genius Marie Curie, working in a drafty shed in Paris. She and her husband Pierre investigated a strange phenomenon they called radioactivity. They discovered that certain elements, like uranium, were unstable. Their atoms were spontaneously breaking down, releasing immense amounts of energy in the process. They discovered two new elements, polonium and radium, which were millions of times more radioactive than uranium. This was a paradigm shift. Matter wasn't static, it was dynamic. It could transform, decay, and release the energy locked within its core. This discovery of radioactivity and the subsequent understanding of nuclear fission with the splitting of the atom unleashed the atomic age. It gave us nuclear power, a source of immense energy that could light up entire cities. It also gave us medical imaging techniques that let us see inside the human body without surgery, and radiotherapy to fight cancer. The secrets held within the atom's nucleus were now in our hands, bringing both incredible promise and profound responsibility. The world would never be the same again. So, from the atom to the elements, to the energy within, we unraveled the fundamental rules of our universe. But the story doesn't end there. This atomic revolution continues to accelerate, powering our future in ways those early pioneers could only dream of. The same principles that Curie and Rutherford discovered now allow us to design materials at the atomic level. Think about it. The silicon in the microchips powering the device you're rewatching this on is a direct result of our understanding of atomic structure and electron behavior. And now, we're entering an even more exciting era. Scientists have discovered mind-bending new materials, like graphene. What is it? It's a single layer of carbon atoms arranged in a honeycomb lattice. It's 200 times stronger than steel, harder than a diamond, and 1,000,000 times thinner than a human hair. Imagine flexible, transparent touchscreens, ultra-efficient solar panels, or even space elevators. Graphene and other 2D materials are pushing the boundaries of what's possible. Our deep knowledge of chemistry is also crucial for tackling our planet's biggest challenges. We use sophisticated sensors to monitor atmospheric chemistry, tracking greenhouse gases, pollutants with incredible precision. This data is vital for understanding and combating climate change. We're also developing new catalysts that can break down plastic waste or convert CO2 into useful fuels, turning our waste problems into resource solutions. From developing life-saving pharmaceuticals to creating sustainable energy sources, the atomic revolution is happening all around us, every single day. The journey from a simple idea to manipulating individual atoms is a testament to human ingenuity. It's a story that's still being written, with new chapters of discovery waiting just around the corner. What new materials will we create? What new energy sources will we unlock? The secrets of matter are vast, and we've only just begun to explore them. The next breakthrough could be anything, anywhere, at any time. Thank you so much for joining me on this incredible journey through the atomic revolution. If you found this as mind-blowing as I do, hit that like button and subscribe for more deep dives into the science that shapes our world. Let me know in the comments what future tech you're most excited about. Until next time, stay curious.